All right, so today we're going to talk about optimization. So I want to back up for a second. So the class is about energy and transportation systems modeling. And systems modeling is really an amalgamation of a lot of different approaches and skill sets. So a lot of the techniques that we're covering or will cover, these are not kind of meant to give you expertise in these areas, right? Because you can take several classes on optimization, right? And so really what we're trying to do is give an introduction to concepts so that it's not totally a black box and that you have at least some familiarity to be able to do some of these techniques kind of at a basic level. And that being said, right, if optimization particularly appeals to you, or any of the other sort of techniques like looking at energy economics or regression and data analysis, I can give suggestions about how to dive into those topics further. So with that being said, we're not going to cover all aspects of optimization, but hopefully this will be enough of an overview to get everyone sort of comfortable with what's going on and how this would be employed in some of the systems models that we're going to look at down the line. All right, so what is optimization? So finding the best available values to achieve a specific objective, and this is sort of most often over a set of constraints. So who's done optimization before? Has anyone done some optimization today? Yeah, today.
Between the hours of midnight and now.
Yes. Yeah, exactly. So everyone does this, okay? Because I know this because you're all here in class. You guys made it here without getting lost and so on and so forth, right? So optimization, you're probably, to get to this class, you probably took the shortest or sort of semi-shortest route between wherever you were before and this classroom, right? And so that is an example of a type of optimization, shortest route planning. But generically, where you were trying to find the sort of best route, right? We can turn this into a more generalized problem where we're looking at sort of the best of whatever it is that we choose. So how do you identify that a particular problem is an optimization? So these are sort of fairly different, we'll call them objectives. How do I mitigate emissions at the lowest cost possible? How do I maximize profits for energy production? How do I use my plug-in hybrid with the least gas and most electricity? How can I minimize downtime for Uber, Lyft drivers? So anytime you see the words like maximize, minimized, greatest, highest, most, or conversely, least, lowest, these are all indicators that you are essentially trying to do an optimization problem, right? Because these actions sort of dictate a sort of fundamental point in your objective that you're trying to get to, which is exactly what optimizations are meant to solve for. Okay. So to give some structure here, this is the canonical form of an optimization problem, which we call negative null. So there are large classes of different optimization problems, but this basic set right here is telling you essentially how to set up a problem mathematically. you have three essential things in an optimization problem. Well, I shouldn't even say that. The first two you'll always have, and then if you have constraints, which is very, very common in optimization, but not always required, the constraints can be an additional piece of your setup. Okay. So the objective function is what you're trying to do, and you're always either minimizing or maximizing your objective function. So in negative null form, you're always minimizing. And if you think about this, if it was going in the other direction, you could just make this negative, right? So if it was something that you wanted to maximize, you could just set up with a negative in order to minimize it, and it's equivalent mathematically. The decision variables is the thing that you're allowed to play around with in order to reach the smallest or largest value of your objective function. And so you have to essentially figure out the correct value of the decision variable to minimize the objective function. And then you could, your objective function and your decision variables could both be subject to constraints that will, prevent your decision variable from getting too large or too small or negative or whatever it is, right? And so, for example, the example that I gave earlier about reducing the total cost to do energy production, that looks something like this. So your objective is to minimize the total cost, and the total cost is equal to the amount of energy that you produce times the cost to produce that energy. Okay. And the thing that you're allowed to move up and down is your energy production. And so I can set this to be really large, really small, right? And that's what this is referring to with respect to this. So that means that, so energy production is which of these three? Decision variable, perfect. Okay, so then let's say we didn't have any constraints. How would I minimize total cost? What should I set energy production to be? 0? Any other guesses? Negative infinity, right? Because there's no, so you could have a constraint that says energy production has to be greater than 0, in which case I would set it equal to 0. But because this is like unconstrained in any way, normally then mathematically, if you ignore the sort of context of the problem, you would just set that to negative infinity. So then thinking about, how are we sort of making this make sense? Well, actually, I would probably want something like, I would probably want a constraint where I have energy production has to be greater than or equal to energy demand, something like that. And then you have a bunch of different technologies, so it might be sum over each of the technologies. Okay. And in this case, let's say there's some total amount of demand, then I wouldn't be allowed to set energy production to negative infinity because I have to meet some energy demand as a constraint. Okay? Make sense? Any questions? Yeah.
Is this only apply to continuous functions then?
Yeah, so I'll talk a little bit about other classifications of problems and sort of, yeah, we'll get into that. Yes.
The negative no.
Negative null refers to it's this form of optimization, basically. When you have your optimization problem set up mathematically in this way, it's known as negative null. And the negative part is because you're minimizing. Yeah. Okay, any other questions? So you can have essentially 4 general classifications of optimization problems where it can be unconstrained, you can be equality constrained. So what that means is in the constraints, all of the constraints are equality. So in the previous example where I said energy production has to be greater than or equal to energy demand, you might instead say energy demand has to be equal to the energy production. And similarly, you can have an inequality constrained demand where you have less than or equal to, and then you can have a general constrained optimization where you have both. And the reason for the distinction is because if you get into the sort of mathematics about how you actually go about solving them, all of these will take slightly sort of different approaches. Yeah, and we don't really get into that. We won't really get into that. And if you're interested in the sort of math behind this, then take an optimization course. Okay. So this is a very crucial concept in optimization. And let me talk a little bit about this. So there's 2 types of things to keep in mind. So convex function and convex sets. When you have a convex function, here you can see if I vary a value of x, then my objective function changes in some way, right? So as my energy production goes up, then in that example, then your total cost goes up, right? And so that might be an example of a linear function. In order to determine if a function is convex, visually we can represent that in this way. So if you have your objective function look like this, a convex function means that any 2 points along this this function, it won't intersect through itself. And so is this an example of a convex function? No, right? Because if I took a point here and a point here, it would pass through itself. Convex set is a similar type of principle. So if we think about a problem that has multiple decision variables, maybe you're changing like price and quantity or something, and they're constrained in some way, right? So you can map out the set of possible combinations of your 2 decision variables based off of the constraints. And all the convex set means is that in the place where you're allowed to pick combinations of x1 and x2, if you draw a line, it doesn't. All of the points within that line have to be within the set. So this is an example of a non-convex set. Again, the idea isn't to sort of worry about the mathematics behind this, but what we're pointing out here is that there are particular types of problems that are structured in ways that if they are not convex, they make them a lot more complex to solve. And so, you might it might be hard to get the right answer, or you might get the wrong answer and think it's the right answer. And we'll show some examples of that, but this is for kind of awareness. Yeah.
The concept which I think is that a non-convex function will have multiple minimum points.
Yeah. So this thing. Yeah. So you were about to steal my thunder. So let me but that's exactly right. So if you think about this as representing the shape of your objective function, if I wanted to minimize, you would want to find the lowest point. That is what it means to do an optimization minimization. So the way that optimizations solve is usually through a numerical process where I'm usually doing some iterative steps to try and get at the best solution. So one of the most common ones, for example, is it's called gradient descent. And basically you say, okay, I'm just going to pick a value of x. Let's say we start right here. And then I'm going to do a process taking the derivative to look at the slope in sort of any direction that I can go in x, right? And so if you go that way, you say, oh, I'm going up the hill. But if you go that way, you say, oh, I'm going down the hill. And so the gradient descent will say, okay, let's take one step in that direction, going downhill. And so I go here, and then I do it again. And I say, okay, if I go that direction, I go uphill. If I go that direction, I go downhill. So I'm going to do that until you get to here. And then you look on both sides and you say, if I go that way or that way, I'm going uphill. So this must be a minimum. So this is your answer. Okay, but what if I started over here? So now I'm going to take a step this way because that's how I go downhill. You end up here, you look both directions and you say, I'm going uphill both directions. So this is my minimum. So this is known as a local minimum, and this is a global minimum. And in non-convex problems, you always have a chance of getting stuck in a local minimum. And there's no way to tell that your local minimum is a global minimum. Well, there isn't totally no way to tell, but very often you can't know. So there's lots of procedures about how you could like get around this, right? You might solve the optimization many times at different starting points for X. You start here, 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 and then you just figure out which one's the lowest, right? Do you have?
Just speaking, is the global minimum meant to be at the actual area as opposed to where it intersects on the function?
Yeah, so this would be your global minimum. This is like a global minimizer starting point. But yeah, I don't know
But
why.
the global minimum line is meant to be at the bottom. So that's
Yeah, yeah. Yeah, that's right. That is weird.
Because the other ones intersect.
Yes. So this is your global minimum.
And
That's right.
the global minimizer is the what?
Yeah, so if I started here and I used if I started here and I used a sort of gradient descent algorithm, then you can get to the global minimum. Yeah, yep, yeah.
When you say that a non-convex function with a given domain and any sort of optimal you find there, could that be a global point within the domain, or would it still be local?
There's no guarantee that it's local because you cannot search infinite points, right?
If you're just given a domain, then you call it local. If you give it a set of points on the x-axis, decision variable.
Yeah, so okay, so let me give you an example of this. So what you're saying is that you're saying if I am confined to x1 and x2. And my function looks like this.
Can you call any optimal point within this domain a global or optimal within that domain? Is that something?
Yeah, so you'd think so, because you might think that your line looks like this. And in certain contexts, that would be, you could say that, but it's possible that you have a very complex function and that you miss something. So if you're doing gradient descent and you take these steps and you figure out like this is your lowest, like what if your function looked like this? So I'm still going to intercept all of the points, right? But you can't search an infinite space, even in a constricted domain. So it's possible. It's so what I'm saying is that, yeah, oftentimes when you restrict a domain, you do get a good sense of the global minimum, but it's not a guarantee. There are definitely problems where even in a constrained set that you're gonna run into these issues, yeah.
Also, sometimes we'll get to check the so the domain and see if there's matching.
Yeah.
The second order derivative has to affect towards x1 and
It's a good idea.
Yes. Yes.
So, like in practice, why can't you actually graph it? It's too like numerical complex, or too many dimensions.
Yeah. So definitely not possible to plot. So yeah, typically it's just too many variables and too many constraints. So like I'll give you an example. A lot of the work that I do works on simulating the operation of our electricity system. And so you have about 20,000 generators. And if you want to simulate it over the course of an entire year, that's 8,760 hours. So the number of decision variables I have, just about how much they turn on is 20,000 times 8,760. So you're talking about on the order of what? Oh yeah, sorry, I have one too many. Yeah. So about 200 million variables. Yeah, 200 million decision variables, and that's just the part of the operation of the plant. And then there's all these other constraints and so on. So oftentimes you're operating in the tens of thousands, hundreds of thousands, millions of variables and equations. It's why optimization is really powerful, but it's not something that you can easily visualize. Yeah. And actually, the interesting thing is, even visualizing a small problem like this, you can kind of quickly see where you run into problems even in like a small, sort of small domain. Okay. Any questions about this?
Is gradient descent the same as extreme seeking?
As what?
Extreme seeking.
Extreme seeking. I don't think I've heard that before.
A similar function. But it's not the same.
Yeah, so you're gonna make me remember gradient descent on the spot here. Gradient descent, you take the like first derivative and then you subtract a set, No.
Did you set it to 0, take the first order derivative, set it to 0, then do the second order test?
No, the second order test only happens at the end, right?
Once you put zeros, then you can
Yeah.
find if it's a.
Yeah, that's right.
So with the second order test, we would put for a non-convex.
Yeah, but it's also like some functions aren't going to be like traditional.
Yeah,
So it might not
they're
be
not
able to take
continuous,
a
maybe.
derivative. Yeah, I mean.
Yeah. So exactly. So
Yeah, well, price.
yeah, so that's right. So there are a whole suite of different types of algorithms, solving algorithms that are meant to solve different types of functions and optimizations. And so, generically, there are ones that will solve certain classes of problems. So I'll put this up for a second and I'll walk through this. And then there are like super common, there are some optimizations that are really common and that are so prevalent that people have figured out either analytical solutions, which means you don't have to do this iterative optimization, numerical optimization process, or have like really streamlined algorithms to do that. And so one common example that people often forget is in optimization is linear regression. So has anyone done linear regression before? A couple people. Yeah, so linear regression, ordinary least squares, least, right, is a good indicator that you're doing an optimization process. And so that is actually a specific type of optimization that has been, let's say, solved in a way that you can do it analytically. Okay, so this goes back to an earlier question about whether functions are continuous. And so that's mainly what we had been talking about here. We're sort of operating in this space. But you can also have an integer problem where you have variables that that instead of being continuous take on a discrete value. So an example of this might be, okay, for one that I do, it's startup shutdown for a power plant. A power plant can be on or off, and then there are properties associated with the power plant if it's on or if it's off for certain amounts of time, right? And so you can only represent that using zeros or ones. Like, what would it mean for an on and off switch to be like 0.7? It doesn't, there's no physical meaning behind that. So integer is a common type of value you can do there. Like another example might be if you were deploying, if you're deciding to deploy like infrastructure, like a charging station, right? And you say, oh, at this location, should I build a charging station? And if so, how many? You can't build half of a charging station, right? So an integer would just be discrete sets of values. These are a pain in the butt. Okay, so if you, yeah, so you'll, if you want, you can take entire classes just on figuring out how to do integer problems. Like, just to give you a sense, like if you had a linear program, a simple linear program that you added like one like set of integer variables, you could like completely make it impossible to solve. So yeah, integer and then mix, which is where you have both continuous and integer. These two are, we'll say, hard problems. Yeah. Yeah, so you can say, so let's say you have xgen t as your decision variable. Then you would have a constraint. Actually, does anyone want to give it a shot here? Any ideas how you might do this? Yeah.
like a natural gas plant,
Well, yeah, generic plants.
there would be amount of, so you have to ramp up to a certain capacity that you want, that's being required for contract from ISO.
Yeah, she's asking like mathematically, how would you write this?
Oh,
Anyone? All right, so xt gen minus x, or sorry, or yeah, minus could be fine. T minus 1 gen has to be greater than or equal to, or sorry, we'll say less than or equal to. I use my, I'll talk about my notation in a second. Ramp dot gen or something like that. So I use x's as my decision variables and c's as my parameter values. So this is a constant that describes an attribute related to like the amount. Yeah. So you could have this as like a so if I had G or comma G referring to the type of generator, you could have that. So then you would have a different ramp for a nuclear plant, a different ramping rate for a natural gas plant. So something like this. Yeah, C would be the parameter. I do so sets as subscripts, X's and C's describing either the variable or the parameter, and then the description of the variable or parameter as a superscript. That's how I do it. There are a couple different sort of standardized like notation methods, but this is a common one, and I think it's pretty clean. So
C in this case is that's the total, that's the actual capacity of the plant.
No, this describes the ramp rate of your generator.
So it's the ramp.
So
in
yes. So for example, this constraint describes, let's say you have we're looking at G for a particular like nuclear plant. Okay, let's say it's a 1 gig plant. What is the ramp rate of a nuclear plant? Does anyone know? How much can we get in one? Let's say T is an hour. How much can you ramp a nuke in 1 hour? Like, let's say 10%. Okay, so then this value would be 100. Okay, and all it's saying is that in time period 1, between time period 2 and 1, I can't go. This can't be over 100 bigger than what I had in the previous time period, right? Yes.
And the reason why you don't have the differential x divided by t is because you have to 1 time interval, like over 1.
Yeah. Wait. Yeah. This is it's what this is our 2, and this is our 1.
And if they weren't 1 apart, you have to divide by the time difference. Like let's say if it was between hours 10 and 1, you have to divide by that.
No, so actually, because this is generically described as not a specific hour, this refers to the difference in every consecutive hour for the entire set. So you can never, well, you can compare 10 and 1, but yeah, exactly. Well, you wouldn't have to do it out. The computer would do it out for you. But this is kind of the power, right, of doing this, is that I can describe the difference between every generation set across my whole optimization, and have that constraint in there. That would be constraining the ability of that. So you will never ever see, because of this constraint right here, you will never see something like this. So gen T, so 1, 2, 3, 4. Like this is not a feasible solution.
That means it's exposed.
It would be infeasible is what it's called.
Is there a separate set of transfer down?
Yeah, so you would just have the other way, right?
And each hour will have a different
Nope.
That would be the same rate.
rate.
Yeah.
Is that true?
That's like,
I
That
think
really
that's true.
it's, I feel like thermal, you have lag, it's like. log or something.
Yeah, well, I'm kind of simplifying it. But yeah, to just I think so don't focus on like the specifics of like what I just wrote out. What you should be trying to take away here is the and this takes practice, but it's like the ability to formulate a mathematical expression for some kind of thing that you're trying to describe. Okay, so that's really the art of this, because the computer will do the solving, but you have to come up with how to do the formulation correctly.
So you could technically just plug in, like the first hour might be 10%, by the hour 5, it might increase all the way to like exponentially.
Yeah, so basically I think it's the same thing that you're saying, right? Is that like if the if the ramp rate is non-linear, then the way that you set up your constraint would be different. So that might be, so for example, if the first 50% of the nuclear plant could ramp at 10%, and then the last could ramp at 20% per hour, then the way that I would change this is I would say for all x gen that is less than 0.5, right? And then you could have, this could be ramp gen 1, and then you could have a CG ramp gen 2 that applies to all x gen greater than 0.5. So for example, so again, what I'm trying to demonstrate here is that like, you have to be able to figure out how to translate what you have in your head into a mathematical equation.
If I may, for you, this is like too much in detail. Like at the level of what you're doing,
Yeah.
policy making, do you ever go to this level?
So the context of your problem depends on what you're trying to do. Like if you are doing some analysis that's informing policy, like the detail about ramp rates may be extraneous, but if, for example, this is an important component of your analysis, then it is something that you'd want to make sure to include, right? So like if you're doing like electric vehicles that can suck up load from the grid and can flexibly do that and deal with nuances about like generation ramp rates, then you would definitely want to include that in your analysis, right? So you should scope out your problem and devise it in such a way that you're trying to do the most like correct and relevant analysis possible. Do you have a question?
I guess that sort of answers it. I was wondering if you got, false minima often by doing something on the cruder side, like having this kind of specific cutoff between these two slopes, rather than a smooth function.
Yeah. Yes. Yeah. Definitely. So that's going back to here. As you think about the structure of your variables and the structure of your objective functions, right? Like generally more complex, right? Like this problem is by far the hardest to solve, right? And so you may even say, okay, even though it physically doesn't make sense for something to be described as continuous, like let's say number of charging stations, maybe if you change it to continuous from integer, it's like a close enough approximation to the answer that you would get out of an integer solution that you say, well, that is worth the trade-off in computational complexity to actually being able to solve it, right?
Some analytic solution, for example.
Okay, so well, yeah, possibly. Okay, does everyone know the difference between, I feel like I've said this a couple times, so I want to make sure that people understand the difference between an analytical solution and a numerical solution. So a numerical solution is, let's say, kind of a kind of brute force approach. I shouldn't say brute force, but basically where you're solving something iteratively in a process where you approximate a solution, whereas an analytical solution, you are deriving the sort of correct answer, usually by just straight up solving like systems of equations. So analytical solutions will always give you the correct answer, but the problem is that the sort of class of solutions that you can derive analytically are fairly small, whereas this can be applied, numerical methods can be applied to any class of problems. So you're lucky if your problem can be solved analytically. And in fact, I should even say that even if there exist solutions analytically, they're not always the sort of best approach. It may still make sense to do it numerically. So a common example of that is actually linear regression. Usually in the types of things that you guys will learn about linear regression applications on, you do the like OLS estimator, which is an analytical solution. But when you get really large data sets in machine learning applications, they actually go back to using gradient descent because it's less memory intensive. So yeah, there are examples of problems where analytical solutions are actually still less favored than numerical. Okay. Let's do an example. Yes.
How is those methods that you mentioned compared to, say, multi-objective genetic algorithms?
Yes. Okay, let me, so there's genetic algorithms and then there's this multi-objective thing, which is different. Okay, don't let anyone fool you otherwise. There's no such thing as multi-objective. And lots of teachers are gonna try and fool you about this, but they're wrong. Multi-objective means that, so you have an objective function here, maybe you have other sets of objective functions. So one example could be, I want to minimize the total cost for my energy production, but I also want to minimize my sort of total like carbon output, something like that. That might be a so-called example of a multi-criterion objective. But really, you end up just plugging it into the same thing and you have like weights on your different objectives. In the case that I just gave, everything just comes out in dollars. So it's still solving one objective function. There is no such thing as solving multiple objectives at the same time. It's just one objective function that has multiple terms. So
The part where you weight your variables
yes.
for each objective space for each objective.
Yes.
But ideally, if you're getting like one per algorithm, right, you're gonna get like several ones.
Yeah.
That let you analyze the trade-offs.
Yes.
So if you don't find it useful.
No. That is useful, and that's like a real thing. I just don't think it's a multiple objective. It's still one set of objective functions. I don't know. I'm being pedantic here, but yes. So multi-objective means that you have multiple objective functions, right? And then you're just weighting them. You have a choice about what you're doing to weight the comparison between different objectives. Okay, your other piece of that was a genetic algorithm. So there are different types of solvers that apply to different things here. So like gradient descent, like simplex, right? These are types of algorithms that you can apply to one of these 9 squares. Genetic algorithm, I'll just say it's a type of solver that's meant to solve like some of the more complex versions of these, and it does some clever things to do that. Yeah. Yes.
I think you could think about these kinds of solvers as being as having more of a deterministic character, and then genetic algorithm.
Yeah, that's right.
So I guess the question that could be useful is, do you have like any advice of what type of problem you would?
Yeah. I'll talk about that. Yeah, I'll talk about that later. Okay. So let's do this example. So this is just a silly sort of optimization example I came up with. And we'll walk through how to solve it and everything, but kind of like what I was saying before, I think the real kind of skill to learn here is to figure out how I turn these 4 statements into into a mathematical formulation. So, okay, I run a small milk and cookies operation. A cookie costs 25 cents to make. And then you purchase milk from a wholesale distributor for 10 cents. You hire a marketing team, and you've determined that the quantity of cookies, which we call Q1, are in demand as a function of the cookie's price, P1. So Q is equal to 0.5 minus P. Similarly, you've determined that the quantity of milk are in demand as a function of the milk's price, Q2 equals 1 minus P2. Rejoice, ye economists, right? Well, let's see. Okay, so what prices do you set to the milk and cookies to maximize profits? All right, so what are our decision variables, or what are all of our variables and parameters here, and which ones are the decision variables? Anyone? Yes. Okay, great. So we will have some kind of objective function, and then we'll have something like with respect to P1, comma P2. What is the thing that we are trying to minimize or maximize? Profits. Great. So we're going to say maximize profit, which I denote as big pi, or minimize negative profit. Okay, so what is this? What is profit equal to? That's right. So almost.
P1 times 0.5 minus P1, and then P2 times 1 minus P2. You said everything in terms of your decision variables.
Well, let me finish setting up just this part. So how do I, if you are someone selling stuff, what is the profit that you make? It's how much you sell times the price minus the cost. Yeah. So P1 minus C1 plus Q2 P2 minus C2. Yeah, and my C1 is, let's say, cookies. So this is 0.25 and this is 0.1, which is the milk. Okay. And then you can always, and then if you want to set everything in terms of just decision variables, you can plug in these values, right? 1 minus P2 and 0.5 minus P1. Alternatively, I just thought about this. You could have your quantities, you could actually have your quantities be decision variables and then use this as a constraint. It's the same thing. Okay, so that's the most important part, is thinking about these, thinking about this text and then being able to set up my negative null form here. Because then for you guys, then you just plug this into like a program, right? And you'd be able to solve it. So once the optimization is set up here, then we plug in our values for Q1 here. I set this up, or I simplify it into this, and then I minimize my profits for negative null form. So I multiply this whole thing by -1. So then this is my objective function, which I am solving for. Yes.
It seems like the milk and cookies are completely separate. There's no crossover, right? So is there a sort of a point doing a combined analysis here instead of milk analysis and cookie analysis?
Oh, good observation. Wait for it, because they're going to get combined later. This is our example 1, and we'll have an example 2, which you'll see. Okay, so some properties here. We actually, you can actually tell that this objective function is convex. If you were to plot this out, you would see that it's convex. And so a lot of the issues that we were talking about with more complex optimizations, you don't necessarily need to worry about here. Because the first mathematician who actually, no, there is a specific reason for this. Actually, does anyone know? Yeah.
Probably just keeps going up.
No. It's the same thing if I were to say maximize this versus minimize this. It has to do with, oh my gosh, I'm trying to remember. This is way back when I was in grad school. So there's, when you do the derivatives of these, the first and the second derivatives, doing the negative is aligns with a, yeah, let me get back to you. It has to,
Marginal cost equals marginal revenue.
no, it's like a math thing. When you do the first and second derivatives,
Usually when you set these to 0, the marginal revenue is marginal cost. That's what I thought. Why do you sort of minimize minus point instead of maximize?
no, it's about,
It's the second derivative best consistent.
yeah, it's like when you do,
First derivative is 0. That just tells you that you're at a flat point in your graph. And then if you minimize all the time, then you're looking for specifically positive.
yes.
Positive second derivative. It doesn't it doesn't become negative for any value of your.
Yeah. Yes.
specific variables.
Yes. The second derivative test is easier and more consistent. Like these days, it actually doesn't really matter if you're maximizing or minimizing in any like engine or solver that you're doing. You just say I'm minimizing or maximizing, and they just multiply by -1 internally to figure it out. But yeah, there is a mathematical reason why we consistently do negative null form as opposed to positive null form. Is that even a thing? I don't know. Okay, but actually going back to what you were saying, so how would we, if we were to do this by hand, who knows how we would do this?
The first order derivative test set it to 0, find stationary points.
Yep, exactly.
And then test those points with the second order test.
Yes. So this basically tells you if you have located to a local maximum or local minimum. And so if you take the partial derivatives, set them equal to 0, solve for P1 and P2, you'll get these values. And this will tell you that you are either at a local minimum or a local maximum. And so then you have to do second derivative tests to make sure that you're actually at the minimum. So not expecting you guys to know how to do this or memorize how to do this. But the idea here is that if the second derivative is positive definite, that indicates that your solution is at a local minimum. And the way that you do that, so after your first partial derivative, you do each in combination with the other partial derivative. You get this matrix, which you can take the determinant of, and your eigenvalues are positive, which indicates that you are at a minimum. Again, this is not something that you would be expected to know for the class, but you know, if you took an optimization class, this is like the simplest first set of things that you would do in solving. And you can imagine, so the idea here is that as your problem becomes more and more complex, right, the ways in which we solve them, like we wouldn't be able to do these analytical approaches. We would do some kind of numerical approach. And so for you guys, it means using like some kind of software to solve it. And so let me go ahead and show a couple examples of different software that you can use to solve this. Let's see. One second.
Alan,
Yes.
question, go back to the previous slide with the H equation.
Yes. One second. Yeah.
So isn't there any instance where the test is indeterminate, where it's sort of reflection or saddle point, you don't know where exactly what the nature of that stationary point is?
Yes. An inflection point. I haven't thought about that in a long time. Yeah, no, I know. So the maximum, so saddle point, you can tell. I think this becomes negative, right?
Thought becomes negative, but then
Yeah.
how do you know, then what do you classify that as? Does that mean the function has no local minimum or maximum?
Well, all you would know is that at that specific point, you're not at a minimum. That's all. You can have other points, right? Like this might not be the only solution. You could have multiple values for P1 and P2. So you would test them all and figure out which one. inflection, what happens at an inflection point here? I don't actually remember. That's like not a really, that like doesn't happen in practice.
That depended on P1 and P2 and change sign depending on where you were. That's
to the direction that you came from. Yeah, that's right. If you ever have a real problem with a inflection point, I'll come find me. I'll give you $10. Yeah. Okay, so we'll start with Excel. Okay, so I can set, so Excel is going to solve this numerically. And so the answer actually was 0.375 and 0.55. And so let me just set this starting point to be 1 and 2. Okay, so we have some profit here. And so profit, if you look here, that is just the objective function that we wrote out mathematically. I put that there, and then you're referencing your decision variables here. These are my 2 decision variables. I don't know. Maybe, huh? This thing here,
No,
you can't make that bigger.
you
I
can
can't,
you
like,
can just do it on like if you go into the cell itself, it'll show you the cell.
Oh, yeah.
Yeah, just need cells.
Wait,
Just like F2
F2.
or F4. F2 will get you in the cell field if thing set up. If not, you just do function.
Okay.
There you go.
I've become a boomer with Excel. It's amazing.
The entire financial system held up.
Sad. Well, I hate Excel, so. No, I use R. But okay, anyways. P1 squared minus 0.75 times P1 and so on and so forth. This is the objective function that we made. And what you can do is you can go up into data, yeah. And you click on the objective function value where your function is defined, and you click solver here. Some people, if you haven't set this up, it's an add-in that you have to add on that you have to do. So it might be not on your Excel by default, but it's easy to add. Click solver.
So it's called solver.
Yeah, it's just called solver. Oh, and it showed up on this screen for some reason. So let me show you what this looks like. So we can set our objective, and then by changing variable cells, which is in reference to your decision variables. So I'm saying these 2 are both things that I want to be able to change. And then solving method, the default uses this nonlinear solver. It also has a simplex for linear problems, and then evolutionary is like a type of genetic algorithm. Yes, which is what we want, because if you look at this equation, that's the minimize equation, not the maximize equation. But yeah, if I had left it the negative of that, you could just say maximize instead of minimize, and it'll multiply it by -1 for you when it does its internal solve. So all you do is you hit solve, and voila. I have minimized my negative profits, and then you've got your 0.375, or and 0.55 for your P1 and P2, which are the values that we had arrived at analytically. But wait, it's not 0.375, it's 0.374, 99952, and 0.54999,865. So did you have a question?
So this is how many that you need to sell to minimize your profit?
No. This is the price that you set to minimize your negative profit,
Oh.
AKA to maximize your profit. Yes. Because you are doing an analytical solution, so this isn't exactly what's happening, but I'll just give you like a sort of example. So, right, so if you remember, if we have something like this, and I start here, and I take a step in this direction, and I go here, and I take a step in this direction, and I go here, right? So you step closer, and you can step closer, maybe you step over the line, and then you go back that direction. So there's essentially, you approximate that minimum, and there is an epsilon term that's like basically telling you, okay, you're close enough, and then you stop. And so that's why you're not getting an exact solution here. You're getting very, very close. And that epsilon term can make a big difference because, you know, if it's really big, maybe you take a really big step in one direction and then you start ping-ponging like this, right? And you could actually go outwards. And so that is a one sort of thing you can play around with in more customizable solvers.
So what is your epsilon?
In Excel, you probably
I
can.
know it's like not the other, that the actual value. That would be like one millionth or something like that.
Yeah.
Yeah, it's 0.0000001.
So, here it is. Yeah. So it yeah, constraint precision. There's some setting
Yeah, no, sorry.
in here.
Like how far it is.
Yeah.
And the power of itself. It's limits, so.
Yeah. Okay. So that's how you can solve it in Excel. Really quickly. In R, you can ignore after line 7. Let's see. And I'll post all of this online. You can set up your function here and put it into a solver called Optim, and you can see what happens here. Tells you a bunch of properties about it, and then here are my values 0.375 and 0.55, and then your objective function value. The last one, sorry, what? Yes, it'll all be online. Yeah. So you can have like a rough template of these optimization forms in different software. The last one I'll mention is GAMS, which is what I primarily use. There's a free version, but it's generally a commercial solver. But the nice thing about this is that it basically takes your formulation directly you can just plug them in here and write it out kind of as you did mathematically, and it'll solve it for you. So yes, I'll put this online and you guys can take a look. Okay. Back to here, not to that, hang on. Okay. Let's turn this into a slightly more complex problem. The local cookie mafia has demanded that you keep the prices of your cookies below 50 cents per cookie to ensure fair competition among other cookie businesses. So you're now subject to some racketeering. The Milk and Cookies Business Board has also come to the decision that the combined price of both items must equal 70 cents. So now, what prices do you set to the milk and cookies to maximize profits? Okay, so we have the same thing that we had before. So minimize negative profits, which is equal to the negative of Q1 times P1 minus C1 plus Q2 times P2 minus C2 with respect to P1 comma P2, but now we have constraints. So I'm going to have ST, which stands for such that. Okay, what are my constraints? Great. P1 plus P2 equals 0.7. That, oh, sorry, wait, no? Here, she was referring to this one. Come to the decision that the combined price of both items must be equal to 0.7. So P1 plus P2 equals 0.7, okay?
Should be less than equal to 0.5.
Yes, so cookies. So P1 is less than or equal to 0.5. Exactly. So now we have a slightly more complex optimization problem, and all we've done is we've added these two constraints. Again, that was the hard part, is really just being able to do this translation into math. Well, that's the hard part if you're like using a computer, because then the rest of it gets solved. Okay. Yes.
Is it also viable to just alter your Q1 equation to reflect the price cap? So instead of having it be just a linear equation, you have it be piecewise.
What do you mean?
Consumers might want to buy cookies for more than 50 cents, but they can't. So it just makes it.
Oh, yeah. So how would you do that?
I guess we do Q1 equals just equals 50 cents for a certain range, and then equals.
Okay. Yeah. Actually, you are you are qualitatively describing one of the primary methods that's used to solve inequality constraints. So we're going to talk about that, actually. I'm actually debating on whether or not we should cover that, but we'll go through it quickly. Yeah, so very clever. So we're solving this by hand. It's once you've introduced constraints, this problem gets slightly more complicated to do. So here's our our negative null form, now including these constraints, right, as I had just written them out. So this is an inequality constraint, and this is an equality constraint. The way that you would be taught how to teach this, or how to not teach this, how you would learn this in a optimization class. So this is a super traditional method of doing it by hand. This is called, you would transform your objective function into a Lagrangian, and then you'd use what's known as the KKT conditions, the Karush-Kuhn-Tucker conditions, which are a way to describe first order necessary conditions for any nonlinear formulation to be optimal. Okay, and I'll just walk through this. Again, this isn't something that you would necessarily need to know. This is kind of high level overview of what like basics of how to solve these things. So there's 4 KKT conditions: stationarity, primal feasibility, complementary slackness, and dual feasibility. What you were talking about is a separation to look at inequality constraints, which gets divided into if it is a slack constraint or a binding constraint, which means that you're right up against that 50 cents or it's in the domain below that, and we treat those differently. And so you test both of them individually in the way that this is solved. Okay. Lagrangian looks something like this. You have your objective function plus essentially these like eigenvalues that are multiplied against each of your sets of constraints. Yeah.
More constraints, does that mean more Lagrangians you have to set up and more KKT conditions? And is there a theoretical limit to how many KKT conditions you can solve with either Excel or?
No, so your KKT conditions are the same, but if you have more constraints, it just makes your Lagrange.
Right, so
yeah.
Under 1, 2, 3, 4, 5, any number of constraints.
Yes, exactly.
So is there a typical limit on how far that can go? Or you could have any number.
Well, like, yeah, exactly. So, yeah, but practically speaking, right, people do Lagrangian and KKTs because you're in a class and they want to teach you how to do it by hand. But like, no one's working on research and like, let me solve this by hand. I would just take that and plug it into R. Right?
There are 2 types of slack, which is in the domain, and the other that is against.
Oh, okay. It's so what I was describing there is we had that inequality constraint. So the price has to be less than or equal to 50 cents, right? So if your price is equal to 50 cents, that means you are like right against the like barrier of your domain. And so that is referred to as a binding constraint. That means the constraint is like holding you back, right? Kind of. And then if the price ends up being naturally less than 50 cents anyways, that means it's almost as though you didn't need that constraint in the first place, right? So that is a constraint where you have slack. Does that make sense? Yeah, so practically speaking, like this can be as big as you want. You probably will want to stop solving this by hand if you're above like 3 constraints, right? Or that would be like the biggest that you would see in like an econ homework, probably, unless.
We had 5 of them. That's just rude. 5.
Yeah, rude. Yeah, I agree. Your professor's kind of a, yeah. Yeah, so like no one does this by hand unless you're like learning how to do it, right? So, but solving by hand, you set up your KKT conditions, right? And your Lagrangian looks something like this. So what's going on here? I have P1, P2, I have lambda, and I have mu. So I have 4 variables and 3 equations, but actually with this, right, you have all of these equations. So basically you're taking the partial derivatives of your Lagrangian and of your lambda and your mu, set them equal to 0, and now of those 4 variables, I have enough system of equations to solve it by hand. Okay, so oh no. Oh, I probably did this by hand and then filled these in. Okay, well, anyways, you can, so the tricky part of this is what you were referring to. If you are binding or non-binding in your inequality variable, you'll have 2 sets of prices, and then you just have to see which one ends up with the lower minimum for your profit, and then that would be your answer. Okay, yes.
Are you gonna ever expect us to know how
Do it by hand, do it-
Man.
Don't do it by hand.
Yeah, I'm kind of, I haven't written the homework yet. So in previous years, I do make people do it by hand, but I'm kind of like questioning how useful it is. Stay tuned to find out. We'll see. It won't be that hard if I make you do something by hand. But yeah, maybe it'll be more.
We'll do it. But some of us are not engineers.
Yeah. No, I think, yeah, I do want to focus on it being useful. So I think, yeah, I'm leaning towards focusing on getting you guys to do the formulation part of it, as opposed to solving it. But that doesn't mean, don't take that as a guarantee. We'll see how I feel. Yeah. So similarly, right, I can solve these with Excel. So here, okay, hang on. I know you can't see it. All right. Here, same thing, same setup up top, but now I have 2 constraints, and these constraints are just exactly what I was describing. So, right, okay. I forgot to cover this. Negative null form for constraints, you also set equal to 0. So P1 greater than or equal to 0.5. Negative null form is P1 minus 0.5 is greater than or equal to 0. And the other constraint, P1 plus P2 is equal to 0.7. Negative null form is P1 plus P2 minus 0.7 is equal to 0. So you do have to set this up like this, negative null form for Excel. And similarly for this one, we can see, as I described here, it's P1 plus P2 minus 0.7, okay? And now if I head on back to here and go to the solver, which always opens on the other screen for some reason. Same thing here, our objective, B3, we change P1 and P2, which are these cells, but now I can add constraints. And when you add constraints, you get to specify less than or equal to 0, greater than or equal to 0, equal to 0. So that's in there. So it looks something like this if I hit add. So you would just reference the cell, set the equality or inequality for your constraint. Okay, so pretty straightforward.
Gives you the options of it. Drop down menu.
Yeah.
Less.
Yep, exactly. And this would be the answer that you get. And we can see, again, if I start at a different point and I solve there, we should get that negative 0.19 or something, whatever that answer was. Solve. Yeah, there you go.
These various programs work with non-convex functions.
Yeah, I'll show you in a second. In R, you can do similar type of thing, slightly more complicated. Use a package R solution P. And you can put in values like this. Again, I'll post this online, but you can see here, if I solve it, it tells you all the information about the solve process. It even gives you the Hessian value and your lambda and your mu values. And then these are up there are your decision variable values, 0.2625 and 0.4375. Those are the prices that you would set. Okay. Any questions about this? PARS stands for parameters. It's not a good descriptor because it's your decision variables. Yeah. It's not, I mean, okay, I guess it's generically your ending parameter values, but yeah. Yeah, so generically, so don't, yeah, generically, we'll refer to the values that change as your decision variables and the constant values as the parameters. The reason why it's called parameters is because this is like your static final value, right? Okay. So back to here. So analytical is essentially solving by hand, although you can also solve by hand numerically. Iterative methods are guessing and checking in a smart way. So across different types of problem classifications, we can solve them using slightly different approaches. So linear programs, simplex, interior points. These are just a couple examples of typical algorithms that you can make. Unconstrained, NLP, constrained, nonlinear programming, gradient free, and then the stochastic might be like a genetic algorithm. Yeah, and so this is far from a totally solved field, right? The sort of more complex ones really explode in complexity. There are a couple famous like problems that that if you came up with a good way of figuring out how to optimize them, you would be rich immediately. Yeah,
So there's no like categories of types of problems that you would solve with each.
that these are the categories right here.
Yeah.
Whether if it's a constrained nonlinear, constraint, unconstrained nonlinear, a linear program.
No, like energy systems will always be constrained, for instance.
No, not always. But so okay, hang on. Let me see.
Like, I think
Actually, I probably should have talked about this, but is this a is this linear, nonlinear convex or nonlinear non-convex, and is this continuous, integer, or mixed problem? Yeah, hang on, sorry. Nonlinear, okay. So this is nonlinear and it's nonlinear convex. You might have to, the ability to determine its convexity is experience. You'll might have to figure that out kind of on your own. I mean, there are ways to check for convexity, but complex problems can be difficult to check. And then continuous, right? There are no integer variables here. So we are working in this domain right here, okay?
nonlinear between the square.
Yes, yep.
And then complex,
Convex is that thing with the cone,
well, because that's the shape.
this thing, yeah. So it doesn't have more than one minimum. Yes, it does not. Yes.
Continuous.
And then it's continuous, so we're here. Okay. So the basic idea is that like these 9 categories will have different ways of solving them. And these are sort of generically some ways of doing, these are generically some algorithms that people use to solve them. Yeah, some very smart people have come up with these. Huh? He's all right. Do you guys know about Danzig Wolf? You guys heard of this guy? So he, I think it was Simplex. So he was a grad student in Berkeley in the like 60s or 70s, and he was late to class one day, and his professor had put up the homework problem on the board, and so the homework came, and he couldn't finish the problem that was presented on the board. A couple days later, he goes to his professor's office and he turns in the homework and he says, "I'm really sorry, this homework is late. It was like really, really hard." And then the next night, he was woken up at his apartment by his professor pounding on the door. And it turned out that the professor didn't put a homework problem on the board. It was a unsolved problem on how to do, on how to solve a class. Yes, yeah. Goodwill Hunting is based off of Dancing Wolf. Danzig. It's Danzig Wolf. Yeah, so he came up with, I think it was Simplex, which basically let them solve any class of linear optimization problem. And yeah, he was like trying to figure out what his dissertation was going to be, and his professor was like, "Yeah, just turn in your homework, and we'll use that." It was like a 1-page dissertation. That's how famous it was. Yeah. So optimizations are big deal. They help with a lot of things. So solving with software, these are a whole bunch of like classes of algorithms that have been used to apply to specific types of problems. And you can see what solvers can be applied to classes of problems. So linear, integer, integer linear, mixed integer linear, convex nonlinear, and so on and so forth. Yeah, and so Excel can do these. Technically is able to, but Excel is a terrible, terrible solver. And I would be very careful with it. And I'll show, we'll show an example of that in a second. But yeah, so depending on what you're doing, you would apply sort of different classes of solvers to them. Cplex is probably, you know, in my experience for a lot of what folks do in like graduate research, if you have any sort of linear system, Cplex is a go-to for that, and you can get that for free as a student. And that can solve linear and mixed integer linear problems. Okay. So GRG, Excel uses a numerical method called generalized reduced gradient. So the solver can fail for a lot of reasons. So it can get stuck in a local minimum. It doesn't have enough gradient information. So, okay, so stuck in a local minimum, we've covered that, right? You're in a pit. I walk in one direction, I'd go uphill. I walk in another direction, I'm still going uphill. So I'm stuck here, even though it's not the local minimum. No gradient information. That is referring to, let's say your function looks something like this. What if I'm over here and I take a step in this direction and it's flat, and I take a step in this direction and it's flat, and I look both ways and I don't know where to go because I'm stuck. Not enough information on the direction. Gradient convergence at extremely steep slope areas. This is a tricky one. It's like if your gradient is really vertical, basically, it can kind of trick up the algorithm because it doesn't know, it can't get to like a different value when you take a step, kind of. But yeah, so the really dangerous thing about this isn't that it just breaks, is that it might break and you wouldn't know. And so you're getting a wrong answer and you think that's the right answer. So let's take a look at an example of this. Okay, here's an optimization problem where we are trying to minimize the surface area of a cylindrical pill, and you are allowed to change the height and the radius of the pill. Okay, so if you shrink the circle, then well, wait, hang on, let's see. Sorry, there's one important constraint. Or there are a couple important constraints. So your radius and your height have to be positive, and we have a volume. So this cylinder has to meet a specific volume, which is this. So 10 inches cubed, so you have V equals VT. So if you shrink the circle to maintain the same volume, the height has to get bigger. And so that increases the surface area of like the rectangle represented by the cylinder, but it shrinks the surface area of the circles, right? And likewise, you can shrink the height really small, but then so that rectangle of this pill becomes small, but then the area of the circle becomes really big. So there's this trade-off that you're doing between shifting the height and the radius to get the same volume. Okay. And so I can start at some kind of guess here. I don't know. Let's say we'll start at 5. We'll just start both of these guys at 5. And so I'm actually not in the correct volume, right? With these two, it's no longer 10, but then the solver can figure that out for us. So let me go to data, solver. And same thing as before. We have our objective function, which is to minimize the surface area of my pill. I'm changing my radius and my height, and then negative null form of the constraint just means that that the volume has to be equal to 10. It's the volume minus 10 equals 0, and then C8 and C9. So it's just saying that our radius and our height have to be positive. It's the negative less than equal to 0. Anyways. There's my mouse. Hello, there you are. So I can go ahead and solve this. Great. So my answer, the smallest surface area I can get is 25.695. And that gives me a pill radius of 1.17 and a pill height of 2.34. Great. So in this case, I can tell you that it's solved properly, but suppose that I started at a bad starting point. So this is just an example. So whenever you do numeric methods, you're always starting at a specific point and you're moving in a direction based off of like the gradient information, right? And in this case, I'm purposely giving it a bad starting point. So it's a little bit contrived because I can tell you that it's gonna like mess up, right? But in the case, but what ends up happening is when I hit solve, looks something like this. So it's going to keep the same volume, but it's the pill, the circle is going to be really big, and it's basically not going to have any height. I mean, there is a height there. Like if I click, I can find my mouse. Yeah, so it's really, really small. But you can see the surface area is way, way large, but it didn't give me an error, right? Like this is a proper solution and it solved, but this is the danger, right? And again, this example is contrived, but for whatever you do, you may get a problem where you think you got the right answer and you think the inputs were all reasonable, but it's still giving you an incorrect solution. And importantly, you won't know that you got an incorrect solution. And that is the drawback of the bad Excel solver. There's like other information that you could use to like diagnose this problem that would be present in other software suites, especially software that's like designed to do optimization. But in this case, you'll just get the wrong answer. Okay. So just something to kind of like keep in mind when you're doing these types of things. All right.
Is there any standard way?
Yeah, depends on the problem. And contextually, right, you want to choose points that kind of make sense. But, and you also, there are also ways of doing things. There's a procedure called multi-start, which tries to get around some of these issues, where across the like feasible range of your x's, of your decision variables, you might try and choose a range of them so that it covers like the space of values that they could take on. And therefore, you might have a better chance of getting like the right answer. Yeah. Okay, so like I was saying, optimization and this sort of class of studies known as operations research is everywhere. And this goes and pertains to basically every industry out there. And so people who work in this area, like it doesn't just have to be energy, right? It's highly relevant. And a lot of the like remaining unsolved problems in optimization, like if you solve the traveling salesman problem, you would instantly, well, more or less instantly become a billionaire, because that would solve so many like logistic problems, and you would be, that algorithm would be used by every industry out there, right? So yes, optimization is an important concept, and we can apply it to huge classes of problems, including, I think, problems that are relevant to all of you guys. I'm gonna skip this thing. Yeah. So advice for you guys, again, this is like an introduction to optimization. So a lot of the like concepts about how to do the solving itself is somewhat of a black box. We had a look at some of the simpler ways of solving them, but the sort of big takeaways is being able to identify the type of optimization so that you can apply the right type of solver. Otherwise, you might run into issues where either they won't work, or even worse, they'll give you the wrong answer and you won't know that it's the wrong answer. Analytical approaches will always give you the right answer. Numerical approaches will always provide approximations, but usually numerical solution or numerical approaches are more able to approach generalized problems. And then, yeah, if you are actually going to do this stuff in your research, I highly encourage you to, yeah, think about taking specialized classes in this area. Yeah, and we'll see how the application of optimization pertains to energy systems modeling. You can imagine this is super relevant for things like you want to minimize cost of your energy system. You want to like reduce greenhouse gases, right? So optimization, you know, plays a huge role in those types of models, as we'll see later on. All right, that's it for today. Mm-hmm. Oh, there it is.